the chart title, and all this stuff. Yeah, also, I'll show this again real quick. Look at all these options, we got so many cool things, it's so nice.
Gary! I was just looking for this book.
Hey everybody, how are we doing? It is Wednesday. Oh my gosh. Oh, Wacky Wednesday's here? Can't hear the music. Let me make sure the AirPods are connected to the computer. They are not connected. AirPods connected. Let's get those AirPods in. We got the AirPods in. Now they should connect. I hear the music now. Up. They're connected. How are you doing if you're in the chat? Mubot is waking up. Let's send out an announcement and say we are doing some office hours. Get some people in here. Get some work done. We got Captain America today. So, who all is here? If I restart the song, will it start? My ears? I can hear it now. That's amazing. Let's see. Can we get some people in the office hours to swing by and do some work? That's the song today. The office hours song. Log in with my two-factor authentication. Adobe Creative Cloud is updating. Here we are on the 201. Funny, I thought there was a bloop, a lag buffer, but let's see right here. Office hours. Come by and review. Okay, click here. I only have one more day of classes for me this week. Busy day tomorrow, though. Okay, there we are. Let's publish this. Okay. Might do Terry's review right here. Shout outs to Terry. Awesome work on a great review. And so we are pulling up the review. Where'd the review go? No! Look at what's coming up, do. Still gotta move an assignment for 207. Canvas content, Proctorio. Canvas content number 2 is already passed. Canvas content number 4. We're asking about that. We could get that done right now. Canvas content number 4. Let's do that. Close out this. I'm gonna go change this for 207 before I forget. There's always so many things to update. Canvas content. Okay. No one's in the chat yet. Okay, let's take a note on this. That's saved for 207. And let's go here and check out. Hey, Blakely, good to see you. Let's start you 100 points. What do you want to get? Canvas content, please. Canvas content number 6. We're going to do that right here. You got it. Let me take the timestamp. 423. Stamp 201. Canvas content number 4, which is chapter 6. Put these in the future so I remember. Let's go check it out. Okay, we're doing Canvas content number 4, so you can get all the Canvas contents done. Come to Stat 201 for all your Canvas content needs. What is this thing called right here? Blakely, do you know what this thing is called right here? It actually kind of says it. What is this thing called? What do we call this? What is this thing right here? What is this thing? What is this thing? What is that? Does anyone know? I don't know is a fine answer and still gets you points. If the answer is I don't know, that's a fine answer. What is the answer to that? What is that thing called? What do we call it? Remember, I don't know still gets you points. Anyone know what this thing is called? It kind of gives a hint down here. Kind of gives a hint of what this is called. No one knows. It's called a correlation matrix. So a correlation matrix, matrix being like a rows and columns type thingy, has correlations in it of the correlation between A and B, C, D, E, and B and A, C, D, E. The non-interesting thing with this, and we talk about like what's not interesting with it, is what is called the diagonal. The diagonal right here is really where we don't go and think about it because it's basically novel correlations. It's A between A, B between B, C between C, D between D, and E between E. And any variable with itself is one-to-one correlated. Like, what is height's correlation with height? Well, it's 100%. It'd be perfect positive correlation. And so you don't really analyze the on diagonal because it always looks that way. Some correlation matrices, like one of the ones found on my Pearson, actually delete the other side of it because this is a symmetric matrix, which means if you fold it over on the diagonal, it'll look the same. So the information on one side of it is the same as the other. If you can see right here, we could take you and show you this. Whoops. This negative 0.12 is DNA. So if you go to D and A right there, it's right there. Or you go to C and A, it's right here, 0.056, 0.056. So literally, you could have one side or the other. And as the rock knows,
It doesn't matter.
got it, Rock, it doesn't matter. One of these sides is fine and gets you all the combinations of the two variables. So all you need to really analyze when analyzing this is one side of the on diagonal. That'll help limit your eyes to what to look at. And that is all the combinations of each variable with another. So we've highlighted in yellow what our eyes need to focus on now. Now there's a ton of questions that can come out of this. So when you think about what we test you on, because once again, we're getting ready for the test, we're understanding what this is and how to look at it. Like when you see this value right here, this is the correlation between C and A. So the correlation between C and A, whatever variable C is and variable A is 0.056. That is a weak positive correlation. So when we think about strong or weak, strong and weak are how close something is to -1 or +1, and 0 is weak. Now moderate is towards the middle. We usually go strong or weak on this, but anything between this is kind of, it's kind of subjective. 1 or -1 can also be called perfect, and 0 can be called non-existent. But when we think about weaker correlations, they're closer to 0. When we think about stronger correlations, they're closer to 1 or -1. The direction doesn't matter. So the direction is positive or negative. So this is two of the elements of correlation, which is for linear data or for linear relationships. And we see here the strength is going to be strong or weak, and the direction is going to be positive or negative. So any question that asks you something like, what is the strongest correlation? Well, we need to find the one that is closest to 1 or -1. And it'd be between D and B. What is the weakest correlation? Well, that's going to be the one that's closest to 0. Now be careful, strongest could technically be, if this was negative right here, then that could still be the strongest because it's closest to -1. Strength is how close it is to negative or +1. So it's kind of the absolute value of the correlation. And when it comes to direction, it's just positive or negative. So let's look what the question asks and answer it, because we can pretty much answer anything now. The question says, what is the weakest correlation? Remember, we're going to find the one closest to 0. That's the one closest to 0. That is the weakest correlation. It wouldn't matter if it was negative. It's not. But if it was, it would still be the weakest because it's closest to 0. Which of the following is not a way to describe bivariate data? And this is bivariate quantitative. It says it right there. So when it comes to describing data, we have to first know what kind of data we're working with. So we've got univariate data, univariate quantitative, and we have bivariate quantitative. Quantitative. How did I make a mistake on this one? Quantitative. Oh, I don't know how to spell it. There we go. Univariate quantitative data means we've collected one variable like height. So you could put up here, like, I'm trying to understand height. And down here, you'd have like height by weight. So there's two variables in a bivariate relationship. So first, you want to think about what graphics we use to display this. The graphics are going to kind of help you understand what we would use to interpret them. So with univariate quantitative, think for a moment, if someone wants to save for points in the chat, what graphics would we use with univariate quantitative? Once again, one of my favorite graphical displays we have right here, showing you the graphics we use. Take a screenshot or try writing them down for practice. Because the blue is quantitative stuff. The top, histogram Alexander with 100 points right there. Histogram's the classic, hence it's at the top. Box plots are good too, which show the 5-number summary. So 100 points are there, Alexander, great job. So the histogram is kind of your classic, shows shape really well. Box plots hide important features, but show the 5-number summary. Histograms are going to be great for this. So with a histogram, you can really see the shape of a distribution well. So a histogram is going to kind of, we'll draw it over here to the side. A histogram is going to look like this right here, and you can see the shape. With a univariate data set, so we want to go here and talk about the shape first. And we're going to talk about like skew, symmetric, modality, and outliers, things like this. This is all ideas of shape with outliers and gaps and skew and modality, everything right there. Next, we get into center. Now, center is based on the shape, and we either really use the mean or the median. Next, we get into the spread, which is going to be the standard deviation, or IQR, which is the interquartile range, the range of the middle 50%. So think of a range IQR. It's going to do that to me, isn't it? So that is how we describe univariate data. With bivariate data, what do we usually graph for a bivariate quantitative data set? Bivariate quantitative, we usually use what display of data? Bivariate quantitative, two quantitative variables. A lot of people get this wrong. Scatter plot, Gil. Great work, right? We just ended the class for some reason. I don't know why. So Gil, amazing work right there. Scatter plots, not a dot plot. A lot of people say dot plots, but dot plots are basically dots instead of the histograms. So you just do dots. I'm not a big fan of them, but that's a dot plot. A scatter plot is going to be the bivariate relationship between two quantitative variables. That's a scatter plot. Not a dot plot. That's not a dot plot. So when it comes to scatter plots, we're going to analyze the strength, direction, form, and unusual features. You can say them in whatever order you want. Frankly, the best thing to do first is to probably analyze the form of it, because it's either going to be linear or not linear. And that's going to tell us if we can do correlation, because to do correlation, we have to have a linear relationship between two quantitative variables. Hence QQ straight enough, no outliers. Gail, let's make you a mod right here. So we have to have a linear relationship between two quantitative variables. And last but not least, not number 5, but number 4, unusual features, which was once again things like outliers, but outliers this time are things that break the bivariate trend. Direction is positive, negative, or neither. If it does, this one is a positive relationship. If it's kind of flat or parabolic, it's neither. And if it goes down, it's down. Strength is going to be the tightness around the form. So this is strong to weak or non-existent. You have to be careful. Classic question on the test is something like this. If we had a relationship that looked like this right here, is this strong or weak? Remember I said start with form first. That'll kind of clue you in. Is this strong or weak? Say it for some 100 points in the chat. Is this strong or weak? Yeah. Not you, Puppet Shark. Answer's not yet today. Yeah, 100 points. It is actually strong though. So good answer right there, 100 points. It's actually strong. The problem is this one is linear and this one is non-linear. So this is a non-linear. So if we go over here and write non-linear next to it, it has a neither direction. It's strong, and I'll show you why. Strong is the tightness around the form. So since it has a non-linear form, the points are very tight around the parabola. You can make a weaker version of this. So to make this a weaker version, you would spread out the points more around the parabolic form. So here's the same kind of parabolic relationship, but notice I'm scattering the points out more and they still form a parabola. So this is weaker now, but not strong correlation. Good answers, Gail. Let's throw another 100 points. It wouldn't be strong correlation. Neither of these have a good correlation because these are both non-what. Correlation only applies to a certain idea, and I'll highlight that. Correlation only applies to a certain idea. These are associated. These have a strong association. Good things for the test. But they are not correlated because correlation only applies to linear. Great job, Daniel. So once again, repeat and remember, things can have associations that are nonlinear. Correlation is the idea of the linear relationship between two quantitative variables. So we have to have a linear relationship to analyze it properly, and we'd make scatter plots for two quantitative variables. Does that, Gail, does that make sense? And unusual features is like outliers, So this could have an outlier like down here, something that breaks the bivariate trend because there's a parabolic trend in the data. So each of these should be considered separately, such as we should analyze the form. Is it linear or not linear? The direction, does it go up or down, or doesn't really go one consistent way? The strength, is it tight around its form or spread out around its form? Notice how this is more spread out around the form. There's a parabola going through it, the true form of it, not a forced line. And this one right here is tighter around the parabolic form. And there really aren't any unusual features right here because we see the data has the same kind of strength throughout and no outliers. So really good stuff. All of this to say that when you have analyze bivariate quantitative data, shape is for univariate. You'll use strength, direction, form, and unusual features. So strength, direction, form, unusual features. Shape is not used. A strong relationship can have a correlation of 0. True or false? Type it in the chat. So check it out over here. A strong relationship can have a correlation of 0. What are your thoughts on that? Don't worry, 100 points again. The answer is true. The answer is true. You're getting all the points, don't worry. It's true because correlation only measures the what strength. Correlation, this has a correlation of 0 basically. Correlation only measures the what strength. So it's true that a strong, it said association, right? Strong relationship or association. Strong relationship like this can have a correlation of 0 because correlation only measures what strength. This is very strong because it's very tight around the parabolic form. So strong relationships can have a correlation of 0 if the relationship they have is non-what. Like this has a very strong correlation. Oh, my gosh. This has a very strong association, but its correlation is next to 0 because it's a what type of relationship. This one right here that I just drew has a correlation close to 0 because the relationship is non-what? Non-linear, exactly. So non-linear relationships can have correlations close to 0 and still be strong. The blue right here that I'm highlighting is the strength. The more spread out points are, like if I draw another version of this and spread the points out more but still make the same pattern, you see how these are more spread out, like I'm spreading them out more, but they still kind of go in a sine wave pattern. So because they're more spread out, the relationship is weaker. When you make the points tighter around the form, then it's stronger. So the same works for the linear also, that if you have a really strong linear relationship, the points are tight around the line. This is the linear strength, or a weaker relationship, it's going to have the points more spread out. So the first one I drew right here is stronger because the points are tighter, and then the second one I drew is weaker because the points are more spread out. And it works for nonlinear forms too. It's just that correlation only gives you the value of the linear strength. So it's only going to properly assess the strength of those. If you do it on a nonlinear relationship, you'll usually see something close to 0, especially if there isn't any sort of linear component to it. So strong relationship can have a correlation equal 0, very true. Strong correlations would not have correlations equal to 0, because then it says it. Strongest negative, we did this earlier. Check out the start of the question here. We drew a little thing to help us out right here. So check out the very start where we started the campus content, where we mentioned that both sides of the matrix are the same values because it's a symmetric matrix. And we have the correlation between things like E and A, EA Sports. It's in the game. Some people know what I'm talking about. And so with this right here, these are novel correlations because it's the correlation between E and E. And that's really something we don't care about because it's the same. It's like, what's the correlation with height and height? Same variable, so it's one-to-one correlated. Why would we correlate X with X or Y with Y? The ones we care about here are one side of the matrix, and with this, the other side is identical. Like if you look right here, it's the same value. So you can focus your eyes on one side of the matrix to try to find these values. The question said strongest negative. So we'd be looking in this region over here, and we want the one that is closest to around here. The strongest negative would be closest to -1, and that's going to be the answer right there, -0.43. -0.34. I gotta say it right? There we go. A p-value for correlation which is statistically significant implies the correlation is due to random chance. Now, this gets into a little bit bigger of a talk because p-values, let's mention some key things about p-values. What are p-values? A p-value is the probability of your results or results more extreme due to random chance given the null is true. What does this even mean, though? What are we talking about here? Well, when we do correlation, the starting assumption is that there is no correlation. So the null hypothesis is a starting assumption. So let's highlight this right here. Let's highlight the null. Null is going to be no correlation. So when we think about what is likely given no correlation, a likely thing to see would be an XY relationship that looks very random. If there is no correlation, we would expect correlation value close to 0. So R is the value of correlation. An unlikely result would be a much stronger correlation. So we've got a lot of unlikely results over here. Unlikely results for correlation would be something like this. And we'll draw some graphics, a really good positive correlation, a really good negative. Things like this are unlikely by random chance. And when you think about unlikely, what are you saying? High probability or low probability? So you would be thinking that and I gotta write R next to these, R equals. You'd be thinking this is very probable given the null is true. And this is very improbable. This is the most improbable. So it has the strongest correlation given all the points are the same amount. And this is the second most improbable. Now you won't find these by hand. Applets and stuff will find it for you. But if I tell you there's a 1 in 10, 100,000, 10, 100,000 chance it'll rain today, you would say, man, it sounds to me like it's not going to rain today. So the probability, this is what a p-value is. The p-value is the probability of your results. Your result is what you are seeing in the data right here. So this is your result. These are your results right here. Like these are your results. Every one of these is your result, what you saw in your data. And the p-value down here is the probability. Actually, the R is also your result. And right here, your result. Your result is the observed data, and we can quantify the observed data with the correlation coefficient. And so when we say given the null is true, once again, we're saying, what do we expect? If there's no correlation, I expect to see a correlation close to 0. Because if there's no correlation, it's like if I say, I expect there to be bread at home. When I get home, I should see bread. If I expect no correlation, then I expect a correlation close to 0, because that's no correlation. What is unexpected are correlations far away from 0. And it doesn't matter in the negative or positive sense.
It doesn't matter.
All that matters is how far they are away from 0, and the calculations will be done for us on how improbable this is. Back in the day, we had to find it by hand, but not back in the day anymore. So what does this all mean? Well, when we think about this, we're saying, I think what we saw over here on this side of the line, that's over there, is very likely given the null is true. So yeah, what I saw is in line with the null. I'm going to retain the null, not reject the null, fail to reject the null. To say, I'm going to continue to believe that there's no correlation. But over here, we get a result that is so unlikely, we have evidence of correlation. Because to obtain something like this, if there is no correlation, because if the null is true, we should see no correlation. What we saw here is so improbable that we are going to reject the null, no longer believe it, believe something else. We are going to believe that there is correlation. Because if the starting hypothesis is that there's no correlation, then the alternative would be there is correlation. So the left side has a likely result given no correlation. The right side has a unlikely result. And when we say unlikely, all we're saying is p-value. So let me write it here in purple next to this. Unlikely means p-value less than 0.05. And so we'll put a little star here, and these would get the star because I can't draw stars today. And both of those are unlikely. And also another thing for unlikely is statistically significant. So statistically significant. So these results here are an unlikely result by random chance because we shouldn't see something like this if there's no correlation. Unlikely by the 0.05 standard, the p-value is below 0.05. We have evidence of correlation. So yeah, I think two variables are correlated. And going back over here, a p-value of correlation, which is statistically significant, less than 0.05, implies that the correlation is unlikely due to random chance. So this is false. We need the unlikely. We don't think it's due to random chance. Not likely. I wish they put likely there, but it's unlikely. So we should have got a 10 out of 10 and really good review. We'll do one more version of this, but we're gonna need some more questions. What's more questions that we got? Wait, still the same quiz. What is the strongest negative? Find the number that is most negative, closest to -1. Strong relationship can have a correlation equal to 0. That is true. To create a scatter plot, both variables must be QQ straight enough. No outliers, two quantitative variables. P-value for a correlation which implies statistical significance due to random chance. False. It's unlikely due to random chance. Shape is not one of the ways to describe bivariate data. There we go. It should be 10 out of 10 again. I'll go look at the grades after I do it 2 more times here. What other questions do we got? I got 10 out of 10. And what we got? Which follows now what describe bivariate data? It's shape, because it's strength, direction, form, and features. Both variables have to be quantitative. The correlation coefficient is not affected by outliers. Good section to do right here. We got 2 questions that are virtually identical. When it comes to correlation, if you don't trust me, watch this. We're going to show a little demo here. What do we say about outliers and correlation?
Anything is possible!
Remind me what we say about outliers and correlation. Little hints again.
Anything is possible!
Outliers can do anything. 100 points, Alexander, right there. So outliers can do anything to correlation. I already got red class on here. People don't believe me with this, though. So the following correlation, the following announcement, the following correlation is very, very what? Look at it as I draw it. The following correlation is very, 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 very what? That correlation on the screen is super duper what? Linear. I like that. That's the form of it. It's linear. Great job, Alexander and Daniel. And how strong is it? It is a linear, positive. You could even add, not even strong, but the great job, N right there. Super duper strong. Do you see the value of the correlation? Great job, Caroline. We're throwing points out like crazy. Thank you everyone for being here. It is super duper strong. It is perfect because they all follow a line perfectly. So this is the strongest possible correlation. And then one little point brings the correlation to what? Do you see the correlation, what I'm aiming for? I'm playing the game to try to get it. There we go. 1 point has now made the correlation equal to what? 1 point has now made the correlation equal to what? It was perfect. 0 from an outlier. A perfect correlation was made 0 from one outlier. How about if I go down here further? What happens if I go down further than what 0 did? The correlation now will probably become what due to one outlier? A perfect positive correlation is now going to become what if I move the outlier further down? Further down. Negative, you got it. So you can see the correlation up there. It has now become negative. You wouldn't be able to make it perfect negative, just, oh, I'm still on the screen. You wouldn't be able to make it perfect negative because you can't make a line go through it, but you could make it really strong. You could actually make it approach, you keep going further out, it will approach -1 as you go further and further away. It'll approach but never achieve because they can't form a perfect negative line. You could go over here, change it that way. It's one outlier is gonna do anything. We could do the reverse of this, where Brian is trying to draw a super duper what? Look at the circle I'm trying to draw. Well, I gotta do it tighter if I want to make the example work even better. Brian is trying to draw a correlation close to what value? Well, I should have just stopped right there. Yes, close. Brian is trying to draw a correlation close to what value? There we go. Little blob circle. Little blob circle right there. Little randomness. 0. Great job, Gail, right there. That is no correlation, and you can draw a circle around it, and a line would go flat through that. There's no correlation to this. This is a good random, non-existent relationship. But now we take 1 point, and now it's a very strong negative correlation from this 1 point right here. 1 point has made it a strong negative. 1 point has made it a strong positive. What can outliers do to correlation? What can outliers do? Correlation. You know it. You love it. Say it again. Outliers can do anything. Anything is possible. So the correlation is not affected by outliers. That's so false. Outliers can make a weak correlation strong. Outliers can do this to correlation. Anything we put on the test, unless we write tricky questions, which I doubt we have yet, anything is true right there. A strong correlation, a strong relationship, careful, strong relationship can have a correlation of 0. That is true. It would just be nonlinear. Do one more version, but do we have some 10 out of 10s in the chat? Feel free to share if you've hit that 10 out of 10 on this quiz. I've done it like 3 or 4 times. I probably hit. What's the best way to study for exam 1? The review page. Also, we're going to have a Kahoot on Friday. 10 out of 10, Caroline. 100 points for you right there. 100 points. Outliers can make a weak correlation strong. Outliers can do that to correlation, you bet. Weakest correlation in the matrix is closest to 0. So there's the ones closest to 0. Bivariate quantitative data is a scatter plot. Bar charts are univariate categorical. Mosaic plots are bivariate categorical. Histograms are univariate quantitative scatter plot. Correlation is not affected by outlier. False. If correlation is close to 0, this implies that there's no relationship. Ooh, this is the same. Great job, Gail, right there. Let's take a vote. Don't worry if you get it wrong. So this is an anonymous vote right here. Is this question true or false? And then I want you to explain to me the answer if you can. So we're looking at this question right here where it says, if correlation, which is measured by R, of 2 variables is close to 0, this implies that there's no relationship between the 2 variables. I'd have 100% people got it. We'll put it this way. If you've answered the question, you've answered it right. Oh, now it's a 2/3. Now it's a 50-50 guess, almost. Can anyone explain it? Explain this to me. See if you can explain it. I'm going to give it a moment here. Boom, Alexander got it. The answer is false because it would only state that there is no linear relationship. Correlation only measures linear strength. So, and great job there on Kayla level. This is false because correlation only measures linear strength. What is the classic drawing to remember of a strong relationship that has a correlation close to 0? So help me out on the classic, like draw of this, Brian. This would be a strong relationship. And there's many things you can draw, but I usually draw this to show a strong relationship that has a correlation next to 0. What do you tell me the name of the thing I'm drawing? I'm about halfway through it. I'm about to start changing, and this is very strong. It's still strong right now, but okay. This is the classic one I draw to say strong relationships can have correlations next to 0. If you draw a parabola, you can see the strength of it by how tight it is around the parabolic form. There's the parabolic form, but the linear strength is next to 0. So R would be 0 because it doesn't really have any linear tightness around the linear form. Does that make sense right there? So don't worry if you got it wrong. I like to do these questions because then if you get it wrong here, you don't get it wrong on the test. But put this one on a note card because a lot of these show up. And you're here right now, so you're practicing. Put it on a note card. Get those note cards out. What are we going to do next? We've done this quiz a lot. I want to see those 10 out of 10s on Canvas contents. Get those points. Was the answer to the graph one? Maybe. Double check it, Blakely. So for those right there, for this one right here, you need to remember this. So it depends on what it asks, Blakely. It depends on what it asks. When you hear, good question, Gail, I'll say it, thank you. When you hear weakest, you hear correlation closest to what? When you hear weakest, you think correlation closest to what? When you hear weakest, you think correlation closest to what? When you hear weakest. 0. When you hear strongest, it could be closest to -1 or 1. And so be very careful in what they ask. And then always remember that you only have to look at 1/2 of the matrix because the other side is identical. So the other side of the matrix is identical, and these are novel correlations, the correlations of 1 because it's correlation of E and E, which is X and X, the same variable. Like how is height correlated with height? 100%, 1-to-1. So you don't have to worry about anything but one side of the matrix. And I would just start looking through here, like these numbers, these numbers, these numbers. Like, what is the weakest positive correlation here? Tell me the weakest positive correlation in this matrix. Tell me the weakest positive. So if it said weakest positive, so you have to think weakest means closest to 0. Positive means it has to be positive. Weakest positive. Weakest positive. Great job, Giel. Another 100 points. That is the weakest positive. Tell me the weakest negative. Great job there on the combos, Alexander. Tell me the weakest negative. So I'm rapid firing questions at you. So you have to think weakest is closest to 0. Negative means it has to be negative. Weakest negative. And this is just the practice you can do to be like, I could find any answer they asked for. You're right. It's this one right here. Boom. There's the weakest negative. Weakest means closest to 0. Negative means it has to be negative. So weakest negative. Strongest positive. Strongest negative. And that's basically the combos of everything we could do, really. Strongest positive thing, I don't think we usually ask that one because sometimes we're like, it's 1. But we could say like non-novel or excluding 1, what is the strongest positive? Because everything is always correlated with itself 100%, so we really don't care about that one.
It doesn't matter.
So strongest positive would be between B and D because the correlation between a variable and itself is kind of a novel, like we don't care about it. Correlation. For the practice exam, does the practice include multiple exam questions throughout the years or just all versions? It's an exam I think that we had from like 2017, 2018 that we've reused. The exam keeps about the same structure, and the Kahoot is going to be a great way to test your exam knowledge. So check out the Kahoot, do that. And you know, we could finish Terry's review. Should we finish Terry's review? What do people want to do? Should we finish Terry's review? That doesn't rhyme. I thought it did for a second. Did we do that? That's yesterday download. Review. We got pretty far into it. We're right here. Okay, we got review. Unless someone says something else, we'll do this right here. Report Q1. No. We'll do that here a moment. 39, 13, stat 201. Test 1 review. Chapter 2. Okay. So this is chapter 2, dealing with univariate quantitative data. Now, if I had data like this, the first thing I would do with this data is organize this data. I know where this question is going to go. Brian is putting those numbers in what right now? And I'm probably going to check it. See, I already forgot one. Brian is putting those numbers in what? I'd love to just put it in statistical software. You got it right. Order right there. 15, 22, 23. I forgot 18. We're going to count the numbers afterwards, make sure we did it right. 27. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the sad part about this. This is why I love software. Because all these questions in the demo, oh, still got the demo going, don't I? There we go. Oh, I gotta. There we go. Is it? Oh, I'm running core demo still, I think. There we go. There we go. There's the mean, there's the median, there's Q1, Q3. It sometimes uses a little bit different methods. Like if I go quantiles of X and I go type, I remember what type it uses. Sure, this is probably the type it uses. So all these values can be found instantaneously. We'll never have you do things like standard deviation by hand because we'd always use statistical software. It's just a lot of calculations to do, but mean we should know how to calculate. And we give you smaller data sets, so we want problems that take not too long to solve. So the practical way to solve this is to use, did I just delete my numbers? They're there. The practical way to do this is to use software which can solve it, but to report the mean, what must you do to your numbers? Now be very careful and check your work. These are some of the questions I'd be double checking on. How do we find the mean? How do we find the mean? I'll start working on it right now because I'll do everything that you'll do by hand too. But then I'll show software just makes life a lot easier. Well, that's easy. It's going to be 13.1. How do we find the mean? The mean is found via the mathematical formula. The sum of the y observations over n equals y bar. So the sum of the y's is equal to 131 over the sample size of 10 is equal to 13.1, and use your calculator. So you can, if you had statistical software, you could double check your work, and you can see the mean here is 13.1, meaning either we've entered something in wrong if we got it wrong, but it looks to me like we did it correctly. Now the median is the middle number, but there's 10 numbers here. Now to get the median, you need to, 1, put all numbers in order. 2, find middle number. If one doesn't exist, average them. So what I like to do is draw a teeter-totter when I'm doing this on paper, when I used to do it that way. I would go here and go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And I know this might look imbalanced, but there's 5 numbers here and 5 numbers here, which means I'm taking 9 plus 15 divided by 2. Because we have where we need to average them because there's no middle number. So with this right here, the median is 12. There is no 12 in this data set, but since we had 10 numbers, if you think about with 10 numbers, the middle number is the 5.5 number. There is another way, don't listen to this if you don't want to. If you do n plus 1 divided by 2, this is position of the median. It's just its position. It doesn't find you the median, it just finds you the position. A lot of people get this wrong because they do not put the numbers in order. Great job, Daniel. Thank you so much. A lot of people make mistakes on this one because they don't put the numbers in order. So they mistakenly go to the data set and start here and go 1, 2, 3, 4, 5, 1, 2, 3, 4. That'd be really funny if it was still the same median. But this is where they didn't put them in order, and then they have a bad time because they get it wrong. This finds the position of the median as in 5 plus, 10 plus 1 divided by 2 means the 5.5 position, which is right here. This is the 5.5 position. That's only the position though. You then have to average the numbers or choose the number in that position. Think about a small data set here with numbers like 1, 4, 8, and you have 3 numbers. 3 plus 1 divided by 2 means the position of the median is 2, and then you would just go here to position 2, and that's the median. So it only finds the position of the median to say sample size plus 1 divided by 2. Or you can just do the teeter-totter trick. Any way you do it is fine. Make sure to put the numbers in order. If you know a few ways, you can get more tricks. Now, what I don't like, and I don't think we've done one of these on the test, is you kind of get a lower data set and you get an upper data set. And if you look at it as like a top 50% and a lower 50%, the 25th percentile is going to be between those. Looking at your quartiles in the data, you've now divided your data up into this, and you divided your data up into this right here. That purple line up there is right here, and there's 25% of data within all of these. So the way this would look is right about here, right about here, right about here, and right about here. I know I've stretched it all a bit, but it's the amount of numbers contained within each quartile that makes the 25%. So because there's 5 numbers here, we can do the same trick. We can do, I'll erase this sort of extra, really? I've got the eraser up. We can do the same trick to get the median of the bottom 50%. So with 5 numbers, 5 plus 1 divided by 2 is equal to 3. And you're talking about this number right here is 5. So 5 is the median of the lower 50%. Same thing right here, where this is the median here. So we've kind of dropped down to the number data set and done this for the Q1 after 1/4 and Q3. And this is the median, and this is the max, and this is the min, and that's the 5-number summary. So drawing your quarters is usually a big help for that right there. So 5 is the Q1 and 22 is the Q3. And then if we know the IQR stands for the range of the middle 50%, we have to think, where is the middle 50% of this data? So it's the interquarters, and that's 50%. If you had 2 quarters right here, that'd be 50%. And they have to think, after this, you've gone past 1/4. After this, you've gone past 3/4, because each of these is 1/4 of the data. And we're just talking about the range of this data. So when you think about what is the IQR, it's the range of the middle 50%. Just like when we do a range, we do max minus min, which is big number minus small number. The range of the middle 50% is going to be Q3 minus Q1. And you can literally just take the distance between these and think in the positive sense. So it really doesn't matter. What way you subtract them, you'll just have to think it's a positive difference. So the range of the middle 50% is 17. And once again, our output confirms this right here. If we go back to our output, it shows it right here. I do want to point out that statisticians disagree on way to calculate the quantiles. There are 9 different ways to calculate them, hence why sometimes software or computers will give you, or calculators will give you different answers. So it's way number 2 that SAS is using and others use, and 2017 was the last time, or maybe someone else argued on it since then, but you can see different statisticians with different ideas over different times. So really good question right there. That's just dealing with some quantitative data. You could display that in a histogram. So if you think about what I can do with statistical software, I can just go here, hist of vector x right there. And better yet, I can go to library and go to ggpubr and go to gghist and do of x, and there we go. Oh, that's so beautiful. The best data ever. We could add a call to it. Can we go call here? Color equals, we'll go hashtag ff8200. There we go. Well, perfect. And now let's go fill. Fill equals blue. Gotta do lowercase blue. I don't know why it gets mad about that. There we go. Grade histogram plus GG title, my histogram. There we go. Oh, doesn't like it. Plus GG titles, mad about that? Oh no, there it is right there. There we go. All these fun things you can do. This is not super interesting data right here. Just a basic histogram. There you go. It's yeah. Change the bins. Can I change bins on this? Let's see right here. Bins equal 4. There we go. I mean, it is what it is. I'm going to show one last thing right here because I do love this, and maybe someone will be like, yeah, I want to start trying out this R thing. What you can actually do is go to a library Plotly and take your GG graphic and drop it into a GG Plotly, and you can actually hover over the bins now and see the counts of data between it. You can even like zoom in or zoom out or pull the graphic, but you get an interactive graphic for very quick. All these are things that we teach in 320 and other courses. So if you are interested in being better with data, 320, 474, 475, 310, all our courses have different ways of analyzing and handling data. Just read the course description and be like, oh, I want to learn how to do that data. Maybe that applies to my discipline or knowledge base. So here we go. Let's put the next question here. I love data. I need to share this is I love data. Data is the best. I love my wife and I love data. So here we go. We're on the next question. 5023. Stat 201. And it's so interesting because what we were just doing right there, was we were displaying data. And we're talking about graphical summaries, visualizations of data, which are very important. Making a good visualization, a clear visualization of your data, helping people understand the context, because all data needs that. So when we think about what data goes where, we actually have all the answers on this screen. This has all the answers to the questions we're looking at. Now, if you want to ace this, try to draw a little sketch of what data might look like. When you think about a pie chart's going to have slices like this of people who said something like yes or no, which is categories. A histogram has a number line below it going from 0 to 100, meaning it's quantitative. You know what? Roll. Yeah, sure. And here I'll highlight these in green, though, the quantitative. So pie charts are categorical, histograms are quantitative, and a bar chart looks like a histogram. A lot of people think it's a histogram, or histograms are bar charts, but it has like cat, dog, bunny underneath it for the type of animal you want, meaning that that's categorical. So bar charts are categorical, and the number line gives it away. A stem and leaf actually looks a lot like a histogram, where you just have a number line down below. And don't show again. What's some missing proofing tools? I don't care about that. You have a number line down below, and then you have the inner portion or the leaves of it, and the numbers right here representing the values. We could go more over stem and leaves, but it'll show you the numbers. So stem and leaves are quantitative. A singular stem and leaf, not a back-to-back stem and leaf. That's bivariate categorical quant. Anytime you make something back-to-back, stacked, or or side-by-side. Back-to-back, stacked, side-by-side are all ways to make things multivariate, bivariate. So when you see your stacked histograms, that's not a histogram. Side-by-side box plots, that's not a box plot. Or stacked bar charts or side-by-side pie charts. And the stacking or side-by-siding of them is just going to make it an extra categorical variable. So like side-by-side or back-to-back is going to be an extra categorical variable because you're breaking it apart by categories. So that'd be a categorical X split on it when you stack it side-by-side or side-by-side, back-to-back, sure. Dot plots are going to look a lot like your histograms or your stem and leaves. They just got dots going up. So dot plots are going to be quantitative right here. And a Pareto is a bar chart put in order. So a Pareto, it can have extra things, but it's going to be a bar chart put in order, and everyone loves bunnies, then dogs, then cats. Everyone knows everyone loves bunnies. So that's going to be a Pareto right there. So the Pareto is a bar chart put in order, put them in order, Pareto. And once again, I can't stress this enough. If you haven't tried to write this down, write it down. You can see Pareto up there with the bars and pies. You can make a pie chart of your favorite bars, a bar chart of your favorite pies. But writing this down is good practice to learn and to know what graphics go where. It can really help with creating visualizations. Bivariate, so here we are. Got to match things. So bar charts are by their nature categorical. And the idea of segmenting or side-by-siding are categorical in nature too. Box plots are by nature quantitative. I think I reversed the color scheme. Let me go look up here. The quantitative is green. And let's write this as a shorthand right here. We have quant and we have cat. I have selected yellow. There we go. For Pareto, would you put quantitative though? Pareto is, good question, Gail, right there. Paretos are categorical. Yo! Oh my gosh, we got 3,200 points. Oh my gosh. Oh, let's hit the button twice. Yell, thank you. We're all capable of making errors. Thank you so much, Giel. 200 points. Good catch. Nice job. So in the future, it's going to be like, Brian said the Paretos are quantitative. Oh, I'm sorry. So good catch. So we have cat and quant. Let me recode these. Man, this computer's going crazy around here. Thank you for that catch. I was like, what? Segmenting or side-by-siding or stacking are all going to be ways to add in a categorical X. So that's just kind of a quick way to remember it. Like if you're stacking things, that's not like a quantitative thing you're collecting. You're doing it by a different group. If you're side-by-siding, that's not a quantity of like one or two. It's like group A, group B, making them side-by-side. And stacking or segmenting, like segmenting is separating by groups. So all of those imply a categorical variable alone. And it makes it bivariate because you're doing it by another variable. So now we get into a bar chart. And let me try to do this. Like, let me make it so there's a little bit of separation here. There we go. There we go. A bar chart is categorical, as we saw earlier. And here we'll draw a little graphic of this. So this would be two categorical variables. So that's A. And then segmented bar charts look like this right here. They kind of look like a mosaic, but not quite, which means mosaic plots are bivariate categorical. So mosaics are the better version, and they go with a contingency table where the mosaic plot is going to look like this right here, kind of like the stacked or segmented bar charts. And the contingency table is the upgrade of the frequency table where you have the bivariate relationship in here. A scatter plot, we've talked a lot about today, is bivariate quantitative. That's chapter 6. And so that's two quantitative variables. So scatter plot is two quantitative variables right there, C. And, oh, we're doing quantitative in green. And I'm trying to color code this to make it really easy to see. And so that is SOI, two categorical variables, and stacked histograms. Histograms are by nature, and then those side-by-side box plots. So that's going to be B right here. Side-by-side box plots look like this, where you have like a yes/no group. So that's the categorical right there, and then some sort of 0 to 100 value over here, blocking the screen. And then stacked histograms are where you take a histogram like this and stack it on another histogram right here like this. So you've got, you know, like a yes/no group, and then you've got a quantitative 1 to 100 scale right here. And usually the Y variable is quantitative we want to analyze, and we're breaking it apart. So it should be good right there. These are all bivariate displays, and scatter plots are the only bivariate quantitative. Of course, you could always do a time plot if your X had a time-ordered nature to it. Really good understanding of graphical displays right here. Hopefully you can get those. True falses. True falses. I hope people come back and use this. I'll try to promote this video and be like, come on, watch the video. Okay. Simulations mimic reality by using random numbers to represent outcomes of real events. Have you ever heard of RNG in video games? RNG stands for random number generation. You ever play a video game that simulates real life, or simulates like The Sims maybe, and then random events happen? Simulations like The Sims mimic reality by using random numbers to represent outcomes of real events. Like they're gonna generate random numbers, random events happen. This could not be more true. I'm gonna exit out right there. Hey Savannah, good to see you here. I clicked Wacky Wednesdays, meant to give you some points, but Wacky Thursdays are gonna pop up on screen. That is true as true could be. Wacky Thursdays, Throwback Thursdays, Wednesday even. A sample statistic is analyzed to make inferences about a population parameter. How do we figure out what's going to happen in the 2024 election? How would we make inferences to figure out what's going to happen in the election? How would we make an inference? Because the election is the truth of what happens. So the election is over here. This is the election. Whatever happens on election day is over here. So how would we make inferences about this? We'd look at polls. Great job right there. So we would take a sample or a poll, which is a sample of people, which would allow us, when we analyze it, to make inferences about a population parameter. It doesn't go in reverse. It kind of can, but usually we think we take samples to make inferences about the population. So you would poll people to get an educated understanding of how people view the candidates. So this is once again true right here. When correlation is above 0.9 or below negative 0.9, it's safe to conclude that changes in X cause changes in Y. We have some bad words in statistics. Only say the stats bad words. What are some of those bad words in statistics? Does anyone know the bad words in statistics? There's some bad words. What are some bad words? Pause, prove. There you go, prove. Great job. It's quote 2. Forever ago we made this up. Whatever semester this was, here's the quote. Cause, prove, accept are banned words. So we never say that something causes something. You could have a correlation of 1 and it wouldn't show causation because any 2 points will either have -1 or 1 or incalculable correlation if it's flat. So you can't say the word cause. This is as false can be. Like that word alone, like when I see cause, I'm like, I think the question's false. Especially on my Pearson, if I see cause, causation, prove, know, will, things that imply certainty, we don't talk about in statistics. We just show evidence in statistics. Outliers can drastically impact correlation. So you have to know here that this is correlation. And you have to remember when it comes to outliers and correlation, what's the deal with outliers and correlation? What's the deal with outliers and correlation? When you see outliers, can, and correlation, so here's the keywords. Let's highlight the keywords. Outliers, can, to correlation. Anything is possible. So that is as true can be. Outliers can do this to correlation. Now be careful. Outliers don't impact the median or IQR, so you have to be careful. But outliers and correlation, when you see that those phrases together, it's like, well, they can change correlation any which way they want. Correlation is described by shape, center, spread. Correlation is described by what? Great job, Savannah. They impact the mean and standard deviation too. Yep, that's why we don't use mean and standard deviation with them, because if there's outliers, we use median and IQR, which are not impacted. Giel, great job. And why is it false? Giel, good work. I'll show the hints on the screen. It says correlation is described by shape, center, spread. So why is that a false statement? And why is this false right here? We have some notes from earlier. Here's what we did earlier today. So use the information on the screen where it said correlation is described by shape, center, spread. Strength, direction, form, unusual features, exactly. Shape, center, spread is for univariate quantitative data. Univariate quantitative data is described by shape, center, spread. We're bivariate, where we start to do correlation between two quantitative variables. Oh no, knowledge, good to see you. We're a stats class. We have special guest Crash Bandicoot. That's what this is. Wacky Wednesdays. Are you here for Wacky Wednesdays? For you, I hate to say this, we don't have Python. We got R. Very sorry about that knowledge. We're using R here. Python's good too, but we use some R, and we love having people here. We'll throw you 100 points showing up. So Mubot, our friendly neighborhood robot, is throwing out those points. But feel free to ask stats questions if you got them. We talk some stats, draw some data. That's what we do here. We work with data. We're reviewing right now. Next, we have when checking the significance of the correlation coefficient, a p-value of 0.01 would imply the correlation is not significant. That does mean not significant does mean not likely due to random chance. But when is something statistically significant? I'll bring up the notes we wrote today. When is something not statistically significant? When is something not statistically significant? Using R. No, it's so good to have you here. Python's good. So something is statistically significant. I'll highlight the portion right here. Something is statistically significant. Something is statistically significant when p-value is what? Good answer, Savannah, right there. But something is statistically significant when the p-value is less than 0.05. Statistical significance just means, and reverse it. Great job, Savannah, right there. Reverse it. Statistical significance is p-value less than 0.05. And I'm going to go to another statistical software here. Check it out. We're going to pull up our second statistical software of the day. We are pulling up JUMP. JUMP is based on SAS, which is classically used. And we got some Pokemon data right here. So p-values stand for probability. And so if we look right here and analyze the attack and defense of a Pokemon, we can get the correlation. Like with AI? It's going to get pretty crazy with AI, isn't it? But we have to, the thing is, a lot of AI is like next word generation. If you look at how ChatGPT does it and what they've trained it on. So we have to have people who know how to build the AI, how to write prompts for the AI, do prompt generation. You have to know how to understand the output from the AI. And I always say this, if I were to give my nephew access to AI and say, use ChatGPT to solve this problem, would he know even how to talk to it? So you have to have a sort of base amount of knowledge in these concepts to then utilize the AI. It's basically like having the best tools in the world, but having no idea how to use the tools. So having the understanding of statistics makes you better at using AI, which I am pro using AI to solve all these problems, especially write code. Man, writing code is so much better with AI. I'll tell you that much. I write a bunch of code with AI. So check this out right here. P-values are statistically significant when they are below 0.05. So a p-value below 0.05 in statistical output will usually have a star on it. So notice it's calling your attention to these p-values. And what does the p of p-value stand for? Because think about when we talk about a p-value, what words are we using? The p of p-value stands for what? The p of p-value stands for that this quantity we are talking about is a what? Hence down here. The p of p-value means that we're talking about a what? The p of p-value. That's awesome knowledge. Congrats, man. Differential equations destroyed me. Diffie-Q and PDQs. It is a decimal. Great job, Savannah. It is a number contained between 0 and 1. That is true because it's a probability. And the probability can't escape the bounds of 0 and 1. 0 meaning impossible, 1 meaning would happen all the time. We're talking about long-run frequency, the law of large numbers. So when we talk about p-values, we're talking about a likelihood of something happening. Is it likely or unlikely? So if you notice right here, high p-values on this side of the screen, beyond where I can reach into the ether, those p-value, that one 0.88, is a high likely of something that would occur, high likelihood of something that would occur if there is no correlation. Where the p-values over here on the right side are an unlikely thing that would occur. And so a strong correlation is unlikely by random chance, given there is no correlation. And once again, here's the key thing to know, and write this in the chat again to practice. A p-value is statistically significant when it is below what value? You can read my bad handwriting right there. A p-value is statistically significant when it is below what value? A p-value is statistically significant, we usually denote with a star, great job Savannah right there, below 0.05. And that's just a bunch of statisticians who came together and said 0.05 is unlikely, 0.05 is even more statistically significant or even more unlikely by random chance. Great job, Gail, right there. So unlikely by random chance is what we're talking about right here. So the relationship between a Pokemon's attack power and defense is positive, mostly linear, with some big outliers. You can even hover over these and figure out which one it is. You can go to rows and go to subset or tables, subset right here. That is Shuckle. Shuckle has a very unusual defense for its super low attack. I mean, it's basically just like a snail Pokemon, so hey, what you gonna do? This one over here is unusually low, and that Pokemon that's unusually low is Deoxys. So that's a legendary one, isn't it? Legendary Deoxys? I think it's in the Diamond and Sapphire. Hey, I teach college because I like it. No. Thank you, Knowledge, for being here. I teach college because I like it, and I love stats. I love data. I love analyzing results, and I get to do a lot of fun stuff. So that's why I do it. When checking the significance of correlation, a p-value of 0.01 would imply correlation is not significant. So what this would mean right here is that the correlation of, so the correlation, thank you, Knowledge, for being here. We appreciate you, and have a good time. Thank you so much. And Savannah, thank you so much too. When checking the significance of correlation, so here's the thing. Think about this. If the p-value is 0.01, what would that imply right here? If the p-value is 0.01, what would that imply? And I'll give a hint. This is the hint. Or if the p-value is 0.01, and great work, Savannah, right there. It is statistically significant. Doesn't mean it's linear, though. Good answers, 100 points. Linearity would only be assessed, and great job, Bailey, right there. Linearity would need to be assessed by looking at the scatter plot. So to assess linearity, there is a way to do that with p-values. It's called a goodness of fit test, which we don't cover in this class. So lack of fit test. And we have no evidence of nonlinearity due to the high p-value. Not covered in this class. But look at this p-value and tell me, this p-value I'm pointing to over there, that p-value is or is not statistically significant. This is still a p-value. Don't worry so much about the lack of fit test. But this p-value right here is or is not statistically significant. That p-value is or is not statistically significant. Just this one right here, the one above my finger, is or is not statistically significant. Is not, because it's above 0.05, 0.05 or higher. And so this goes beyond the class a little bit, but the null hypothesis for the lack of fit test is that there is no lack of fit for the line. So since we fail to reject the null, we do not have evidence of a lack of fit. So what that means is that the relationship is linear. Now, the way we do this in Stat Tool 1 is we simply look at the scatter plot and think, does the line go through the data pretty well? And this line does look to go through the data pretty well, so it's two quantitative variables, straight enough. But the problem with this plot would probably be the what's. If we gave this to you on the test, we might say, what issues does this have? So think about with your QQ, straight enough, no outliers. And to Savannah, that was such a nice comment. And I always want the positivity here. I was trying to bring about that positivity. I was pushing for that positivity. I was like, we're going to be positive here. And they kept saying no. I said, well, too bad. QQ, straight enough. We say we want no outliers. So we got some pretty big outliers. So the outliers might be drastically impacting like Shuckle over here and Deoxys and things up here. So it's a little bit iffy, and we could do an outlier analysis and all this good stuff because it's pretty neat what you can do. You can go here to residual plots and you see what's going on with those residuals. Don't have normality. Ooh, what is this graphic called? It's got a different name on the screen right now, but what is this graphic called and why would it indicate non-normality? We know it by a different name. We know it by a slightly different name. This is called, let me get more full screen so it covers my screen. We have learned this graphic by a slightly different name called a normal probability plot. And you want to read that backwards, the plot that shows you the probability it's normal. In a normal probability plot, we line up the quantiles of the normal with the quantiles of our, whatever we're looking at, our data. In this instance, the deleted, oh, good, defense residuals. I was doing deleted residuals. This is just your data. Don't worry about the data we're looking at, it's just data. And you notice, boom, you got it, Savannah. If it's normal, it'll follow the line where they one-to-one match up, where the line is the expected normal. It's not that there's a linear relationship in the data, it's that the data matches what is expected given normal. And so this kind of goes against it. If you look over here, especially at the high side, we see a breakaway. So I'm a little bit concerned. At the low side, not so bad. Follows the line mostly. And then over here on the high side, you'd also notice this with the residuals, but that gets into other topics for another day. If one knows the mean standard deviation of a data set, then all the values in the data set can be converted into z-scores. Now, this is a trick question, I think. Let me ask you this way. When do we use mean and standard deviation? I know why students get this wrong. When do we use mean and standard deviation? When data is what? When do we use mean and standard deviation? To find the center, yeah? To find the center and spread of normal data. Great job, Gail, right there. So mean and standard deviation can be found anytime you want. And to find z-scores, the z-score formula is observation minus mean over standard deviation. That's the z-score formula. So I guess technically, well, it's saying you know then all the values, which would be the y's. If you know the mean, which is mu, and you know the standard deviation, which is sigma, could you just find the values? It says can be found. It doesn't say should be found. It says can be found. Like if you know these values right here, if you know mu, if you know your observations, your values, and you know the standard deviations, you can find, yeah, you can find all the values. It's not a should you find them. It's just you could find them. Should you find them? That depends on the shape of the data. So this is true because it says can be converted. So the key phrase right there is you could convert them to z-scores. The straighter the line in the normal probability plot, the more likely the data will pass the nearly normal condition. We should have just said the more likely the data is normal. And Savannah, I didn't know it because we went down to this. But when it comes to a normal probability plot, you were just mentioning it a second ago, you look at the normal probability plot and you ask, does the data follow the straight line? The more it follows the straight line, the more normal it is, and thus you are correct. This is very true. Great job, Savannah. Fill in the table with the correct symbol. Observed data value is y. That is just like my height. If you say Brian is 75 inches tall, that is going to be the observed. Sample average is y bar, and that is like the average guy is something like, we would say like 70 inches tall. So 70 inches is the average guy. So that's the average for guys. Sample standard deviation, that is S, and that would be the variation within guys' heights from a sample. And this would be a sample of guys, like if we talked to 100 guys, they'd be 70 inches tall. And the variation within their heights might be 3 inches. And you could draw out a normal curve, mean of 70, and a standard deviation going up of 3 and down of 3, where you go up 3. So I'd be a little less than 2 standard deviations above the mean. So you can use that information right there with normally distributed with a mean and standard deviation from the data. So you have to think, how does this apply? The mean is the center of the curve. The standard deviation is going to be the units you go up and down. And then the observation right here is going to be where I land. And I could turn that into a z-score by doing the following formula. Observation minus, and we're using sample mean notation at this moment right here. It just depends on how your data is collected. If you would use population mean or sample mean, and you can see the z-score is 1.67 when rounding up to 2 decimal places. So that would be 1.67 z-score. The distribution mean, so I prefer to call this population mean. Population mean and population standard deviation. You'll probably never hear me say, so this is normally distributed with mu and sigma. And this is mu, hence leading into that right there. It just depends. You're saying, well, why would you use mu? Why would you use sigma? Why are you going to knock things off your computer? Mu means you have access to all the data, which means you have the population. If you knew all students at UT, you would have like 33,000 total of in your, not really sample anymore, but population that you took data from. Where if you only have sample data, you have lowercase n. Now be careful, these two are not the same thing right here. That does not mean population size with mu and sigma. It's going to be worded as, well, we never put this on the test. Good question, Gail, 100 points. It's never appeared on the test. I've never, actually, this is the first time I'm kind of seeing it. If we say, we just say population. So Gail, great question right there. I would call it population because it's for all the data. And even I was a little bit like, I hope that's what they mean by that. But I've never used the word distribution mean, population standard deviation for all the data, which is the true distribution. So I guess that kind of makes sense. This is like if you talk to 100 guys up here, this is getting all like 100 students or this. It won't show up like this. Usually we just ask you which of these notations is the population mean, which of these notations is the sample mean. We've done that. And then correlation coefficient is R. And technically, it should say sample correlation, because population correlation is rho. So this is pretty good to have, and I think it's pretty much everything. Can't think of any other notation we've learned so far, but that is pretty much all the notation, and it's really good. I would write these down. I would know them because a lot of them we have already learned. Like, and it could say Q1, Q3, things like that. That wasn't true false. That was the data entry stuff. What other questions do we have for the main screen? Good stuff. We still got 25 minutes. I got new protein bars. Check it out. On time with Brian right here. Oh my gosh. I'm not gonna read the back because they're a little high in fat. That's all right. You need fat. Organs gotta survive. But it's like, oh my God, look at this. Look at this. Man. It's good. Macron? No, it's like Fruit Loop flavored. It's like white chocolate Fruit Loop. It says, now this is adulting. Sure. Sure. Do you have a sponsor? I always think about those things. I've thought about like reaching out to like Monster or Red Bull or something like that. But then I'm like, one, I don't need to start the Monster arc again where I drink Monster all the time or Red Bull. I was a 2 Red Bull a day guy. Like I was a 2 12-ounce Red Bull. Please, I tell you, the coconut one, the white Red Bull, the coconut berry, that is really good stuff. Coconut berry Red Bull, best Red Bull ever. Please try it, or don't if you don't like Red Bull. Same my freshman year, Bailey knows what I'm talking about. And I just can't get on that kick again. Right now I'm a 2 coffee a day with almond milk. So I get my, in the morning I have a big glass of water, have my coffee with almond milk. About before leaving the house, I have another glass of coffee with almond milk. So the almond milk's gonna be better. It's got calcium and all that stuff. Only has like 30 calories per serving. And I put a pretty good amount of almond milk in it. So maybe only getting 20 because it's not like full glass. But it's like 1/3 almond milk, 2/3 coffee. Because I was drinking cream in my coffee and I was like, how much cream am I drinking? Cream is bad for your blood pressure or your, not blood pressure, but your LDL, HDL, high density lipids and low density lipids. I get coffee with oat milk creamer. Sounds nice, Giel. I'd try that. I should mix it up. But almond milk's been pretty good. Will the test mainly be chapter 5 or even it'll be evenly distributed? We can do, let's do some fake chapter 5 questions. We're just chilling for a moment, but I like that, Bailey. 100 points. I drink my almond milk in mine. Yeah, that's been a game changer for me. I mean, I'll drink straight coffee, but it's okay. If you give me a really good flavored coffee, like a really strong hazelnut coffee, I can drink that straight. I can drink straight hazelnut coffee, but if it's like, doesn't have a nice robust flavor, like dark hazelnut flavor, then I'm gonna be like, you give me like a light blonde, I'll be like, this is like watery. Bleh. Or is it, if it's decaf, no way. Not drinking decaf. Don't make me drink that decaf. Let's do a chapter 5 or 2 question. All right, here we go. I need that stuff. I don't want coffee, I need coffee. When you need coffee, that's a responsibility that only an adult can have. Chapter 5 is one of the chapters people get really worried about on the test. Now, there's 2 main question types that really destroy people on chapter 5. So when it comes to chapter 5, the 2 really tough questions that usually get people, oh, I'm sorry, Noah, go back to Red Bull. Or I'm sorry, Noah, either one, if it works for you, Red Bull. Empirical rule questions or applet picture questions. Will you use the applet on the test by going to the applet and clicking on it? Will you use the applet on the test by going to the applet and clicking on it? Oh, Mewbot does that. Thank you, Mewbot. I was gonna show that dude Mewbot. No.
I was mean, Brian. He does not deserve Mewbot. The students deserve Mewbot. Mewbot, out.
Well, thank you, Mewbot. We're here for positivity. Mewbot knows that. So with this right here, we've got the applet. And with the applet up, Mewbot giving out points. People wonder, what would an applet question look like? Well, let's say we're going to collect data. I want somebody to give me something we could collect data on. I'll come up with the rest of the numbers. Just give me something we could collect data on. I'll write a question from this. Anything. You tell me, what could we collect data on? What could we collect data on? Thoughts on it? The Statuon website, Mewbot? Thank you, Mewbot. We could. What can we collect data on? A chess tournament. So imagine we look at years of playing chess, weights of newborn babies. We could look at chess tournaments, and we could look at rank. People have a rank in chess. So average chess rank. So the average chess rank. Ooh, my gosh, look at what? This is so cool. Let's check this. This was such a good thing. See, this is why I ask people for things. That data looks kind of what-ish. I mean, not perfect. It got a little bit Monster Man here. We're reviewing some Chapter 2 Monster Man. Little monster man going on right here. Kinda normal. Kinda normal. Little right skew, but no normal monster man right here. And so with this in mind, we have the mean. We know what the mean is. The mean is given to us. The average rating is right there. So the mean is right about here. And what would you estimate the standard deviation to be? Just give me a small estimate of this. Not small, but so let me see. 100 to 400. And we do about that. You can just go. Yeah. What would you estimate the standard deviation to be? Just take a guesstimate of it. Because this goes down to about 300-ish. This goes up to 2,000. I wouldn't go, so this is 3 standard deviations, remember? Good answers in the chat, 100 points. I wouldn't go that big though. Because this is a z-score of 0, 1, 2, 3, -1, -2, -3. I like that 200, 250. And like, I didn't draw this perfect, but let's see if when we recreate this with the normal applet, if we get something similar-esque, and then we've done a good estimate of the standard deviation. So 450, 500 would make it way too spread out, because usually we go up and down 3 standard deviations to draw the normal curve to where it about hits no data beyond this. Now there can be data outside of this, but, and this is Blitz chess, they're playing fast right there. I think Blitz is the fastest of chess. I kind of know some Magnus Carlsen rocking out in the chess world. So here we go, let's go 200. I'm gonna go 200 because it's nice and neat on the numbers, and look at that. The lower number on this is the exact lower number we saw. Probably due to the right skew, it didn't perfectly mimic it. Yeah, anything outside of 3 is definitely an outlier, and 2 is a light outlier. Like, having a chess rating of 1,500, if this is accurate, is kind of high for this tournament. Like, for this tournament, 1,500 is kind of high, and 1,700 is like, whoa, you are a way high chess player. You're really good at chess. I think Bullet is 1 minute, and Blitz is 3. Thank you, Bailey, right there. Yeah, Bullet is... Yeah. Oh, so Bullet's the fastest, like a speeding bullet fast, and Blitz, they're both just fast terms. So I'm like, what's going on? So I'm gonna write a somewhat hard test question from this. This is a somewhat hard test question. If you get this, you probably can do most of these. Okay. So you were told you are in the top 5% of the chess tournament ratings. What is your rating? Okay. You were told you are in the top 5% of the chess tournament ratings. What is your rating? Where is the top 5%? Just where is? You'll see how quickly we can solve this. We just have to think about the steps. We're not even gonna look at the picture first. Where is the top 5%? Where is the top 5%? Keep going, Noah, go a little bit further. Where's the top 5%? Keep expanding upon what you're saying. Give me more info. The top 5%, as I save this graphic right here, is where? Nice job, Savannah. Savannah's saying where it's between. That is correct. Now, you're wondering probably, how in the world do I have this? When you start your test, you should what the normal curve. When you start your test, you should what your normal curve. When you start the test, you should draw out your normal curve. Now, when you hear 95, your brain probably defaults to the pen not letting you use it for some reason. You're probably thinking right here with, really? Oh my gosh. This thing is possessed. Now we try it again. When you hear 95, I love you, computer. You probably think this. But that's the middle 95. What we are looking for is the 95th percentile. which is somewhere below the top 2.5. Does that make sense? And below the top 16. Because the 95th percentile is the top 5%. Does that make sense? Does that make sense what we're looking for right here? We are looking for the top 5%, which is the 95th percentile. It's not the middle 95. We're looking where the top 5% is because we want to say that there is 95% below this. That's what we want to talk about there, is 95% is below this point. So what are we given in this graphic? We are seeing the what 5%? What are we seeing in this graphic? We are seeing the what 5%? I know that doesn't say 5. The lowest 5%. The lowest 5%. Isn't the answer we want just going to be over here? If only we knew some value at the center of the curve to figure out a distance, this is a way. And then we could just use that same distance over here to add it on. Well, what is this value at the center of the curve? The value at the center of the curve is the what, and I have it circled now, and I'll even say it as notation. The value at the center of the curve is the what? 1100, which is the mean. So we would know 1100 minus some value x equals to what? What would this equal to? So now you have to use the information on the screen to say, well, if we were to subtract x, what would that equal to? Now I got to be careful because I have x written twice because of the way it marks it. Let's just call this y variable instead. And now it'll be more obvious with the notation on the screen if I call this minus y equals x. So this value down here is actually this value right here. Does that make sense? So now we plug in the value and we figure out how far they are away. So we can subtract or whatever we want to do, but we just go 1100 minus 771.03, and there's the answer. So now how do we solve this? I want you to figure out the next step to do, to be like, oh, now we should just what to what, and we have the answer. So if you think about the information you have on the screen, we just need to what here. Or if you don't know, too, but this has all the numbers needed. Boom, you got it, Savannah, right there. Exactly, because this quantity we just found is the distance right here that it is below, and we're just going to add it here due to the rule of symmetry. So it'll simply be 1100 plus that number, and there's the answer. And then we could go back to the applet if we're practicing and just do this, and there's the answer right there. Great job, Savannah. That is a trickier question. If you were able to get that and understand it, that's a good one to get. That's a harder question. Now I can make it even more difficult with an additional step and make it the hardest questions we ask with applet pictures. So we're going to go to the same chess tournament here, and it's going to be even more difficult. This is a level 10 question, I would say. If you can solve this question, you are in the 1% of chess players. Okay, so this is a level 10 question. It says 5th percent. Yes, that's the bottom 5%. It showed the 5th percentile on the screen, and that would be the bottom 5%. So now this is a level 10 difficult picture question. If you understand this thoroughly, you probably can't get tricked by these. I can't promise, but this is about as tough as I could make them. So here we go on a level 10 difficulty question. Let's see if we can do it. We'll do easier questions in class 2, but this is the end of office hours, so let's do some tough ones here. You are in a chess tournament where you are in the top 1% of chess players. The tournament has a mean of 1100 and standard deviation of 200. Now here's the thing. Draw it out. Now notice the drawing you get gives you what's right now. Immediately notice your drawing, and it's up here at top. The drawing provided to you, we can add something to and draw it on our paper, is giving you what's currently. The drawing you have currently is giving what's. The drawing you have currently is giving you what's. Z-scores. Z-scores. Great job, Bailey and Savannah. These are Z-scores. So if I were to draw this out, I'd go down here to the bottom, and I'd immediately start putting in my mean of 1100 and my standard deviation. So this is what I would do here is I would start adding my info, and we see the info on the screen, and I would write this in, and you have it. Once again, I beg of you, start the test by drawing the normal curve. You can't bring it to the test, but draw it out. Start using it on the test, start drawing each one, and you'll notice you can get some good guesses at the answer, and then you can confirm answers. Next, what is that shaded area worth? What is that shaded area on the screen worth? What is that shaded area? We're just marking all the information we have. We're filling out the normal curve before we start diving into the question, seeing what we have and what information is provided to us. What is that shaded area? It's 98. So this is the middle 98% has been provided. And so you just go right here with whatever number this is right here. And that's the middle 98% being, and it can be different amounts because we can put whatever amount we want in there. So it won't always be the 68, 95, 99.7. We can use any numbers. And so now we go over to here and we ask, where is here? So think about what is the value? What are the values at these points? Like what is here and what is here? What goes there? You got it. So those are, and these are what values? What are these values? You can just type one letter and I'll know what you're talking about. Oh, Bailey, 100 points. Bailey knows where we're going with this. Because Bailey said, wait a minute. If you have 98% on the inside, then that would leave 1% in either tail, making this down here the bottom 1% and the top 1%. And if you are in the 99th percentile, where would, or I said top 1%. Oh, well, she just said 99th percentile. And actually, Bailey said right there, the top 1%. So what do we know for the top 1% right now? So we're trying to find the top 1%, right? That is our goal. Find the top 1%. We want to find this. And what do we know for the top 1%? So we know the what for the top 1%. We know the what for the top 1%. We know the what for the top 1% right now. I can tell you the answer to this question now. The answer is 1566.66. We know the what for the top 1%. What is that again? You guys remember what that is? That 2.33 is a what? What is that 2.33? It's a z-score. So what does that mean? The answer is going to be 2.33 standard deviations above the mean. Can you also guesstimate the answer? The answer has to be between what and what. So take a guesstimate of the answer by looking at the answers down below. Take a guesstimate and say my answer has to be between this and this. So as you're solving for it, you'll know that you have boundaries by which you can only give plausible answers. So when you think my answer has to be between certain values, look between what it has to be between, and then also think it's going to be a little closer to that. Does that make sense, Bailey, right there? Let me know if you're stuck on it. So now we've got a plausible guess for our answer. And then what we're actually going to solve for is a reworking of the z-score formula, which will be the z-score formula is observation minus mean over standard deviation is equal to z-score. But if we want to solve for y, it's reworked to y equals the mean plus the z-score times the standard deviation. We are solving for y, which is 1566.66. I'll show that here in a second, is equal to the mean of 1100 plus the z-score of 2.33 times the standard deviation of 200. We enter it into our calculator to show that we did the work correctly, and it will be 200 times 2.33 plus 1100, and there it is right there. Or I added too many decimals. See, shouldn't have done it that way. So there it is right there. And technically, the z-score of this is 2.3263. Makes sense. Good stuff right there. That's just some more decimals on the z-score if you were to carry them out further. 2.3263. There it is right there. I don't know the next one. 5, 4, 4, 8. Yeah, 2.3263. So, and there's ways I could check these because I've done a lot of these. But if you were able to solve this one right here, this is a tougher question. The 200, good question. 200 was obtained why? And I should have marked this to begin with. I should have marked this and should have marked this. There we go. Yep. Yeah. No, Savannah, 100 points. Great job. Don't keep asking those questions. I should have marked those to begin with. I should have marked my mean and standard deviation. So really good questions. Like this full sheet solve right here. Really, as you notice, there's a lot of steps because there's a z-score. Drawing on it, it's going to help a lot. We're going to narrow down the possibilities by looking at the curve and saying, well, the answer has to be between 15 and 1700 because it's a z-score of 2.33. These are the hardest ones because you have to take in all the information and be like, what am I looking at? What does it mean? But good work. So even if you understood this at a decent level, you're getting there. But the applet pictures, the pictures will always have a way to solve it. Empirical rule questions could be something like, we'll just finish with this. Okay, determine how to mean this. Try to solve these as I write these. So we'll just end off starts with this. What is the score of the 84th percentile? So we write on these, use the empirical rule. Use the 68, 95, 99.7 rule to solve. I'm just going to put some questions out here, so I hope you'll watch this in the future. I'll direct them to it. But we write this like this usually in like red text to be like, use this. Try to solve these if you want. I'm just going to rapid fire some questions. What is the score of the 84th percentile? Yep. Oh, this says, what is the chess score? Yeah, you're on the right track with that. Sorry, question 3 is asking that. Question 3 does a z-score as a cheat question. Correct, Savannah. And then question 1 would be, I'll try to do 10 of these really quick. What percent? We'll do 5. Come back. Because I actually want to show the solves for these. So question 1, great job. Savannah is correct because this is 1 standard deviation above the mean for the first one. So when you go 1 standard deviation above the mean, you'd have the middle 68%, the outer 32, and so the top 16% is where the 84th percentile is. That means 84% of the data is below there. So that is correct. The middle 68%, the outer 16s, and 84% of the data is below there. So actually that graphic right there that I just erased shows that the top 16% is going, or 16% would be above 1300. So it's the same answer. What is the z-score of the 2.5th percentile? So 2.5th percentile is if you draw your normal curve, you don't actually have to use the data right here. You can just go to z-scores. And using the z-scores of -2 and +2, the middle 95 is here. And this is where the outer 2.5 is. Subtract from 100, divide in half. and the bottom 2.5 is the 2.5th percentile right there. So it's at a z-score of -2. What percent of people score between 11 and 1500? So 11 and 1500, and do you have this one right here? 11 and 1500 are going to be, if we write our data down below this, between here and here. So the answer is half of what? The answer is half of what for this one? This is the one we're currently doing. The answer is going to be half of what? Good question right here. The answer would be half of what? So you have to look at, we're between 0 to 2 on z-scores. The answer would be half of 95 for this one. Half of 95, because this is between 2. You're on the right track for the next one. This is half of 95. Good answers, 100 points in the chat. This would be half of 95 because you're in between -2 and +2, and that's the 95 right there. The next one adds on an additional area, which is this. So the answer to that one was 47.5. This is 47.5%. It's half of 95. And then this one is the 34 because it's half of the 68. And then you would just take these two numbers and add them right here to get the total area between. So these two would be the area here, which is 81.5. So you would do half of 68 and then add it to the 47.5. Does that make sense? Did some rapid fires here. It's the end of office hours. But a huge thank you to everybody. These are how empirical rule questions could look, where you use the empirical rule, and highly suggest drawing it out. Once again, if you make your own drawing right here, it's going to be a lot easier. So I would suggest drawing it out like this right here. My drawing got a little crazy, but you can then look at the different areas and figure out what's going on. Check out class or other videos where we draw the normal curve and show how to do it. Until then, bye for now, everyone. Bye! We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.